Welcome to this second session of invited and plenary talks that are part of the technical program at SC17. I'm Padma Raghavan, and in my role as the technical program chair, it's my pleasure to introduce Dr. Gordon Bell, who will reflect on 30 years of the Gordon Bell Prize. Dr. Gordon Bell is presently a researcher emeritus at the Microsoft Research Silicon Valley Laboratory. While he's a familiar name to most of us here today as an evangelist for scalable supercomputing, his interests in multiprocessing date back to the mid-1960s with the design of the Digital's PDP-6, one of the first multiprocessors and the very first time-sharing computer. Later, as Digital's vice president for research and development, he was responsible for the VAX computing environment. In 1987, he led the cross-agency group as head of the National Science Foundation's Computing Directorate that made the plan for the National Research and Education Network, or in other words, the Internet. Now, Dr. Alan Karp will provide a longer introduction, followed by an interview. Thank
you. There aren't very many keynote speakers who weren't a warm-up act, but I've been told that's what I am. I'm here because 31 years ago, I asked a really interesting question. In fact, it was such an interesting question, it doesn't even matter that I got the answer wrong. But to appreciate the question, you have to understand a little bit about what the world was like in 1986. So for those of you who are too young to remember, and for those of us who are so old it's getting hard to remember, I'm going to tell you a little bit about what it was like. Now, you know they say that history doesn't repeat, but it sure does rhyme. Well, in 1986, the president was not a reality TV star. We didn't have reality TV star. We were lucky back then. But he had been a movie actor. And when we read the headlines, we had the same ratio we see today of 2 disasters for every political scandal. Now, what has changed is technology. In 1986, this was a telephone, unless you weren't home, and then that was a telephone. If you asked people what a computer looked like, they probably thought of that, but in fact, by 1986, it looked more like that. Now, if the people you asked were part of the 8% of households that had a computer at home, they probably said, what happened? My slides jumped forward about 4 slides, sorry. If they were part of the 8% of people that had a computer at home, they might well have said that this is what a computer looked like. And if this dapper fellow traveled for business, well, he probably brought along a portable computer. What made it, sorry. What made it a portable computer was that it had a handle and it only weighed 25 pounds. Okay? If you talked about the people who were the 1% that connected to a network provider, they might have still been using one of these at the blazing speed of 300 bits per second, but more likely they were using one of these at 4 times that speed. Now, the problem is both of those tied up your phone line, which didn't please your teenage daughter one little bit. Come on. When you did connect, you probably saw a screen that looked like this because the first web browser was still 6 years away. This was an application. Each internet provider, each network provider had a different one of these. And if you look down in the lower corner, you'll see the newspaper. If you wanted to read the online newspaper at breakfast, you started the download before you went to bed and hoped nothing bad happened. Come on. In 1986, this was a supercomputer with 8 really powerful processors. But people were building machines like this with 1,000 really wimpy ones. And that's where we get to my question. We know from Amdahl's law that even if 95% of your program can run in parallel, you still are limited to a speed up of 20. So what are you going to do with those 1,000 processors? Run 50 independent jobs? Well, what I did was I couched my question in terms of a $100 challenge to the first person to demonstrate speed ups on general purpose applications to prove it was worth building a machine like that. Now, Gordon heard about my challenge, and he said nobody's going to take Carb's money. So what he's going to do is he's going to offer $1,000 a year for the best speed up, 1 year after the next. You had to beat the previous year by a factor of 2, just to keep things interesting, I think were his exact words. Well, the first year, we got 7 entries, and 5 of them were right where I had expected them to be. We got 1 that came in, well, you know, there's always an outlier. Maybe it was some weird application. But of course, the Sandia people blew it all away with 3 applications running with speedups up to 600. This is where I got the answer wrong. How did they do that, given Amdahl's law? Well, they made the very simple, what should have been obvious to me, observation that when you get a bigger computer, you run a bigger problem. And a bigger problem has a higher fraction that can be parallelized. And that makes the speed up essentially unbounded. And that's why today we have machines with 10 million processor cores. Now, in a minute, I'm going to ask Gordon to come up here and tell you about the next 29 years. My part of the story is essentially over at this point. Now, Gordon has had quite a career. He's got more accomplishments in it than many of us would have in 2 careers. 3 of them stand out to me. You better be careful with this thing, Gordon. It's going crazy on me. We heard about the VAX. He's probably best known to computer scientists for that. But I bet you he's gotten more popular ink for his ongoing research project, My Life Bits, where he records his life digitally as much as he can. One thing I didn't know about Gordon was how active an investor he's been. And since the startup I'm working for is currently unfunded, we're going to have a nice little chat when I finish here. Okay? Gordon has gotten a whole bunch of awards and honors and whatnot, but the one that stands out to me is the National Medal of Technology. So without any further ado, Gordon Bell.
Thank you. Thank you, Alan. Let's see. Okay. Wonder if I'm going to be able to make this.
If you prefer to use the keyboard, you can just
I may.
use the down arrow.
Wait.
The down arrow.
That's a down arrow?
Yep.
Okay. Maybe that. I can't see the down arrow. Anyway, what it was like in 1987, which I'll point out was a year that preceding the first the supercomputing conference, that I was at NSF starting with a startup, and I like to do startups. And the startup was the National Science Foundation Computing and Information Science and Engineering Directorate. And I was talking to the research community, and I said, parallelism is the issue. We're going to have these machines that are going to be highly parallel, and nobody knows how to program them. And I went against 3 of the key researchers, including Don Knuth, who didn't think we should work on parallelism because it was hard enough to program sequentially. Anyway, the research community at that point said, gee, we're going to have a millionfold parallelism in 2002. Well, it turns out we got that in 2013. And so they were off by 10 years, which is the usual number that researchers are off in terms of how long it takes to do something. As an engineer, I said 100 by 1990, in another decade. And I was off too. So I was off the other way by being too conservative. This is a slide of of the history of all the machines, and the prize is really about the top right-hand box, which is I characterize as multicomputers or clusters. The lower left-hand box, the beginning of all supercomputing, was really dominated by Seymour Cray. So here's one man who really dominated supercomputing for 30 years, starting with the 6600 and then going through introducing vector processors and then multiple vector processors. Now what gets interesting is that little overlap square when people were searching for something that would work. So that was, and now going back, it says that was a good year to start a prize, because that then really characterizes this whole upper right hand up into the right box, which is really all of the machines that are essentially clustered. At the time, that 83 to 93 transitions, when we were in the search for the transition, it was really the break from a single memory computer. Some of the factors included, I'd say, stimulated by the Japanese 5th generation AI effort. DARPA had kicked off a strategic computing initiative. The main thing was that there was a reason powerful, inexpensive killer micros were on the scene that were competing with other machines, and so the clustered micros were really going to be look like an alternative. The nice thing is that we had, at that point, at the end of that, we did have a existence proof, which became known as Gustafson's law, and then the prize, and then later followed by the top 500, really have kept us on this path, or really on a treadmill that turns out to be a factor of 1,000 every decade, or nothing quite evolves like that. And then that was all. At the end of that period, it really was an issue that standards had been determined. MPI, the first MPI standard was in 93, and then the Beowulf recipe came out in 94. So that anyone could put together a cluster. And then all of this is fueled by the need for all of this as grand challenges, because the grand challenges, without that, we can't sell these budgets to Congress to get the money to go forward. Now, it turns out that in that whole period, there were about 50 companies lost their lives in that search from 1983 to 1997. There's too many of them to read here probably, but starting with the French company, and I think ending up with Wave Tracer, and we had a number of everybody trying to find the recipe during that period. If I look back over sort of the history of real early history of computing for scientific computing, and put 20 seminal events in the first couple, or the first one is really the computer itself, the recipe for that, the von Neumann machine and the EDVAC report. And then the second most important thing was Fortran in 1957. So we should be celebrating it as its 60th, I guess, birthday. And if we go through a number of the different first few machines there, first few events, really Amdahl's law comes out, and then the various Cray computers. Then we come with an intermediate era there that I think is marked by a machine called the Caltech Cosmic Cube, and that was built by Sight and somebody else that I can't remember right now. But anyway, they showed that they could easily put 64 computers together with a hypercube connection, and that you could actually program them and get results, and that was very cost effective. Intel saw that, and then they proceeded to proceed along that line. One of the people at Caltech came off from that work and started N-Cube, and that was really the first, I'll say, serious machine that was kicked us off on this on the path, and then of course Gustafson's law, which was stimulated by the first prize, or I won't say by the first prize, by Allen's $100. If you go back and read the report, read the comment of that. In fact, I was thinking this kind of this morning. You know, I think Allen's prize, because it was the one that was reported in the New York Times about that Sandia reported that three different problems had achieved parallelism of 600 to 1,000. That was really the thing that I think moved clusters and our current mode of computing forward probably 5 years. That without that proof, without that stimulation, I don't think things would have, anyone would have been convinced that you could actually use that, and it would have taken much longer. But anyway, that put an end to to the notion that there was a limit there. And so going forward, we see just various kinds of important landmarks, including, as I say, the stimulation, a recipe for Beowulf, and I need to point out that that work, that Tom Sterling's book now on supercomputing, that he started really with the Beowulf standard in 93. He now has a textbook, and that I hope is going to have an impact on the educational part of supercomputing, because if you look into how you learn about supercomputing, it turns out that it isn't really very well accepted still. You know, when I was at the National Science Foundation, there was a definite split between computer science and computational science, or the idea of computational science. And that break, in fact, has gotten a lot better, but on the other hand, it's still hard to find those courses about supercomputing if you go in through the computer science department. And so a lot, I think, still needs to be done in the academic world, and I hope Sterling's book will stimulate that. And then finally, the bottom 20 or so, half dozen things really have to do with various progress, culminating with my last 20th one being the Sunlight computer that has 10 million cores and computes it over 100 petaflops, which I assume that's what's going to be given. A prize is going to be given tomorrow evening about that. Anyway, let's go through these events. This was really important. Fortran, 1957. You can recognize it. 08 was the last standard one I could find. The Cray supercomputer in 76 really was brought in the vector era, and that was by Seymour Cray introduced. This machine, I think, is an important machine. This is the Fenton Tantos desktop Cray 1, which was 40 years after the 72-inch tall Cray 1 or Cray XMP. Here's a 10-inch tall computer that computes at the same speed that has in that bottom an FPGA that simulates or emulates a Cray. So that this is really one of the nicest things. You know, whether I can't tell you whether my watch will outperform that or not, but at least this desktop unit computes at that rate. Here's the Caltech Cosmic Cube, an 8 processor and then a 16 node machine, and then the resulting Intel computers that spawned. And then, of course, Gustafson's law here in 1988 that he posited in '88 was the thing that broke the mentality, the Amdahl barrier mentality. MPI in '94, and then the Becker-Stirling recipe for clusters also in '94 said, here's how you build, anybody can build a supercomputing. Now let me talk about the evolution of the prize itself. Alan talked a little bit about it, but it was very loosely specified in those days, and I think that was a really good thing because it let people be rewarded for different kinds of improvements or design or breakthroughs in computing. Started out on scaling or peak performance. It had to be, with Alan more than 100, but anyway, the first ones was an honorable mention given in '87 for I think an SC17 machine, and then peak performance, price performance, and then compilers were rewarded, and a little later various speed ups. Special purpose machines were rewarded. People building different things directly in hardware, and then languages, and that special lifetime achievement was a prize to get the people at the University of Tokyo who had been building a thing called the grape computers. They were winning every year for price performance because they just put more and more FPGAs together to have a gravitational pipeline that was computing for the n-body problem for celestial algorithms were awarded, and then sustained performance, scalability, the whole time to solution as a metric got in there. And now I think if you read the Wikipedia criteria, it's really for peak performance, and then fortunately it's also for special achievements in scalability, because in a way I think the committee didn't really want it to be the prize to be a surrogate for the top 500, but more in terms of what are the advances in use. At least that was the intent of the prize. If I look at overall kind of some of the selected programs that were run there, the first three there were run at Sandia. The beam stress analysis and surface wave and fluid flow, these were all kind of linear algebra or numeric grid problems. In '88, of course, a QCD, there was somebody who was doing QCD. And what I had learned about QCD is that no matter what machine you have, or whoever's run it, there are always a bunch of people with QCD that are there to absorb any amount of capacity that's available. Sort of, I think I called them the bottom feeders once, but I'm not sure how happy that was. But and then a circuit simulation and a network optimization. Those prizes were, or one of those was won by the Thinking Machines CM2. This was a SIMD machine. I think that had either 16,000, 64 processing element nodes. This was something that, not a surprise that it would be there, but and also not a surprise that was kind of the last one that would have been built. So it was really a point product, point on the curve. Anyway, you go through that, and then in '92, and then later on, that was simulating gravitational star, or a number of gravitational stars. In this case, I think 9 million, and then that went through, and the same thing then was done later than that. That was done on the K computer there. I don't know. I don't have the year. But then the same techniques then were applied at the molecular level. And so the David E. Shaw, Anton 1 and 2 were winners, and they were doing essentially gravitational, but applied at the to molecules instead of heavenly bodies. Anyway, we go on through there, and then the last one, which was 2016, the scalable atmospheric simulation framework is that was done in China is and a special one. So these are kind of how they've evolved. This is if I look at all of the winners, the organizations, or the members of the organization that won prizes, then it turns out that there were 118 kind of awards given for these institutions, and then 64 where there was just one person from a particular a single organization. So Caltech had alumni from, or 7 of the prizes had Caltech winners, and similarly with IBM, and so forth. So this is kind of, where do these people come from that are able to win these awards? The other thing that comes up here is The 87 prize had 3 people who won it, who actually wrote 3 programs, and that was at Sandia. And then the 2016 prize winner there were 12 on the 12 authors on that paper for that. Those little stars, that star up above there that has 45 people on it was the Anton II David Shaw computer that was doing molecular dynamics. If you build your own hardware, particularly that particular hardware, that takes a number of people, so you have a lot more people involved. And these are essentially various prize-winning platforms, starting out with the N-Cube 1,000 node that was done there. And in fact, I have to say that Cray XMP on that same year was the only time I got involved in the prize at all. Was I heard about that NCAR was running whether it was a simulation, weather simulation model, and they had fully utilized 4 processors of an XMP because I thought that was clearly a direction, and so I sort of arbitrarily gave him $1,000 too. I hope to say that we ought to be fairly flexible in what we do. If you look at the prizes and compare them with the top 500, then they track nicely. Namely, that people are getting as much out of in terms of gigaflops as the top 500 indicates. Except you've noticed that the last one, it was about, the top 500 number was about 95 petaflops, and the prize winner was 9.5 petaflops, just because of the difficulty of the difference of a benchmark versus of a really large problem. Now looking at the other interesting curves, instead of absolute performance and floating point operations, here's the curve of the amount of parallelism, how much you're doing at the same time. And it turned out that I think that the prize was important in kicking things ahead 5 years is those first points around 1,000 there and start of 87 really were kind of off the curve in terms of what was the standard way of doing supercomputing with vector multiprocessors. This is a machine last year that had the over 10 million cores, the Sunway, which I assume will be the top 500 this year. And anyway, that was a vast number of, there are 160 cabinets there, and then you put all that together and you got down at the bottom, there's 4 65 node processing elements that are all connected as a single unit. If I look at that, the prize winners there, then this was for highly scalable atmospheric simulation framework, and what's involved there were 4 of the principal authors of that, which included computer science, and then the things about the computing and climate modeling and the mathematics. So at this point, you're getting into a highly complex set of interactions to get the to deal with the performance, including algorithms, especially knowledge of the applications, and then just simply the complexity of making it all work together. In fact, if you delve down on this slides from the team, there are the four basic elements of the ocean model, the atmosphere, and then land and icing, and then those are backed up with a lot more detail. So we're into a highly complex set of interacting components and doing simulation. And I like to point out on the supercomputing question, like if supercomputing hadn't been there, there would have been some question whether climate change is man-made or not. What would you think? You know, we would really be arguing about climate being man-made or not without supercomputing. No question about it. Did I say that? But anyway, at least that's what makes me so smug about it. It's all based on a belief here in computing. These are some of the hardware prize winners. I'd say the hardware is sort of nice surprises, more than I thought there might be. Lots of history of QCD. SIMD works at least once. The PLAs was used in '89 in one of the prizes. Folks at Tokyo Tech introduced GPUs into to computing and were awarded with a prize for that. And then one that hasn't really appeared in any degree yet, which we might expect, is FPGAs may make their appearance in future supercomputing. So anyway, these are some of the questions that that come to mind about what's going to be, and that is how long will the prize be relevant and useful for supercomputing or useful for science to mark progress? Because it really is something to mark progress. Tied in that with the a concern of not wanting it to be just a surrogate for the highest, for the fastest computer, and somebody getting access to that, because that is very limiting in terms of the work. And then I think one of the things I'd like to know, or I think we'd all like to know, is how have the program sizes evolved? What's the effort evolved? You get a little bit of the effort by looking at that last prize with 12 people, and then how the algorithms improve to do that. And then in the future, there will be a different structure with databases. So anyway, let me stop there, and we can get into something else. Thanks.
Have a seat?
Hey, yeah.
So the plan was for me to play Larry King for a few minutes and ask Gordon a few questions. Should we do that or take questions from the audience first, in the interest of time? Okay. Okay. So the first question, Gordon, this is my remote. How did you get it to work when I couldn't?
I'm not as nervous, apparently. I don't know.
We want to switch. We want to switch back to my slides on Gordon's computer.
Okay.
Okay. So I'd like to tell me about your first love. Mine was an IBM 1620 with the most beautiful set of punch cards I'd ever seen. What got you into this business?
Well, I've got to say the first computer that I wrote a serious program for that actually was distributed and used by other people was a machine that Alan Turing worked on. This was a machine called the English Electric Deuce, and it was a machine that was a spin-off of the National Physical Laboratory A's. And then also it turned out that the Bendix G15 was one of the antecedents or the successors of it, but that was it, and I used punch cards, really pioneering or programming in binary. So we fed, and we don't have enough time to explain the machine, but it's something you might expect, a very efficient machine that Turing would have designed. You can look at that, but and that was punch cards, and so from that I went to the TX0, which was an interactive computer.
What year was that?
That was in 1958. I was programming that to do speech research, and what I learned from that was that computers all had to have a screen. They all had to be interactive, and I didn't like cards. I was never going to use a card after that, and I might have learned something else, but
all right.
Anyway.
So we both got the Amdahl's law thing wrong. Now, I never had any training in computer science. That means I learned it the way I learned about sex, on the street corner from my friends.
Right.
What's your excuse?
It was just, it was one of those things of just not thinking, you have in your mind some barrier there, and instead, if you remove that barrier, it all breaks. Yeah. So it was a matter of, gee, we couldn't think beyond the.
And I think we got lucky too, because the rules didn't say the speed up had to be on the same size problem.
Right.
If we had said that, we wouldn't have gotten Gustafson's.
Yeah. And.
Okay. So Don Knuth was once asked, looking back on his whole career, what's the one thing he would change? And without batting an eyelash, he said he wouldn't use floating point in tech. My answer is very simple. I would have offered the $1,000 ongoing prize, and you'd be up here interviewing me.
Oh, okay.
What would you go tell your younger self to change?
I think the fact that I don't have attention span now to do programming is something that everybody's got to pay attention to. Yeah. That is, whatever you're doing, you got to keep doing it. So I'd say mine is really, I'd like to be able to get enthusiastic about building a computer now, but I just don't have the tools to go do that, and don't fall into that trap.
Okay. We'll skip the last question because I think Gordon has answered it, and let's go ahead and take questions from the audience. So come on up. We have microphones.
We're on time.
If you don't, I got another question, so you won't get out of here any quicker. We got somebody coming up. That's Gustafson.
Yes, hello. Just a comment, since it was so central to a lot of your discussion. The 600-fold speedup you talk about was a fixed Amdahl speedup. The scaled speedup was over 1,000 on a 1,000 processor. So all of our 3 applications got speed-ups like 1,020
Right.
out of 1,024, and 637 if you were forced to keep the problem of fixed size. And I wanted to also mention that I think this had an influence on the top 500 because we're now, of course, using weak scaling in order to adjust the size of the problem. And I had to convince Jack Tongara to stop using 100 by 100, or 300 by 300,
right.
or 1,000 by 1,000, and just let the thing scale.
Thank you.
Right.
Okay, Cleve Moeller.
I got two questions. Where can I get that 10-inch desktop tray?
Yeah.
How much does it cost?
Right now, I've got my hands on it for the Computer History Museum because it's really something that should be there. There's, I think I can introduce you to the.
How much does it cost?
It's maybe $1,000. It's got an FPGA in it, and that's about it.
Okay.
Yeah, it is just one hell of an impressive piece of work.
And continuing about bottom feeders, when are we going to see quantum computers in this list?
The quantum, sometime we've got to give one for quantum, and so I think that's been encouraging because, by the way, I've as an engineer, I've sort of not discounted. I've discounted quantum for me because I think I'm not going to outlive their existence. So, but I can imagine the prize. I think there's still money in the prize.
Well, we might have to come up with a new definition of speed up, though.
Yeah, exactly. But anyway, the first practical problem to get solved on that certainly would be a winning.
Well, I think our time. Yeah. Well, I think our time is up. Let's thank Gordon.
Great.